Hey, what's up, guys? This is Chung here again. So today, uh, we're going to talk about this LeetCode problem 863. All nodes distance k in binary tree. Okay, so it's a medium problem. It has like 1900 likes. Yeah, probably will also give it another like here. Yeah, it's a pretty good medium question. I would say that. So what it does is you're giving a binary tree here. See, this is a binary tree, and then you're giving a target node. In this case, it's 5, and another and the k, which is a distance we're going to use. And you need to find out all the nodes that have this k distance. For example, here k is 2, right? So it means from 5 down the road, from 5, 2 is the distance 1, and 7 is 2. 4 is also 2. So 7, 4 is the candidate. It's also the result. But remember, you can also go all the way to root and then coming back to the right side of the tree. And then 1 is also a candidate, right? Because 0 is 3, so the result will be 7, 4, and 1. The order doesn't matter, so we just need to find all the nodes that has the case distance to this target node. Okay, so what should we do here? And at the beginning, I was thinking, I'll tell you what was my what was my experience about this problem. At the beginning, I was thinking about, okay, so in this case, okay, so it has a left and a right. So first, I need to do a traverse the tree to find this node here, and also if this node is in the left and in right, if it's in the left, and then we have to minus plus this distance when we traverse to the right. So basically, a lot of hassles there. And then Uh, so I think a cool solution for this problem is that in order to treat this one as a tree, we should convert it to a map or a graph, right? See, because see that's the 5, right? So because 5, we're using the 5 as the center out of the graph, and the 3, 2, 6, they're all the neighbors of the 5, and the 1 is of 3, 0 is 1. So 7, 4 is the neighbor of 2. So then this problem becomes calculate the shortest path. I mean, sorry, to calculate all the nodes that have the distance with k with this 5 equals to the k, right? Then it's converted to a graph problem. That's much easier to handle with the left or right, right? So what do we do? Okay, so with that in mind, so first we need to uh, initialize a graph, right? So the graph is default dictionary here. It's gonna be a list, right? Because we're gonna for each node we're gonna be storing all his neighbors. All right. So then we'll have a queue here to traverse the tree so that we can build this graph. So collections.dequeue, and so right. So the root is there. So when you can traverse the tree however you want. You can do a uh but I think keep in mind you want to do it in you want to have process the root first and then the child, because we want to build the the neighbors for each node. So let's in this case we're using a a, a pre-order, which basically we traverse 3 first, and then 5, 1, and then 6, 3, sorry, 3, 5, and then 6, 2, 7, 4. Pre-order means we traverse the root node first, and then the left, and then the right, right? So what do? We graph, right? We pop the node here. Every time we pop the node here, we pop from the left, right? And then we do a if node equals to right, right? That's how we traverse traverse the do a pre-order traverse, and then we just do a q dot append, right? Append node dot right, and then if node equals to left is not none, then we do a left, right? So in the end, that's when the while loop is done, then we finish traversing the tree. So that's the basic of the pre-order traverse, right? And then while we're traversing the tree, what do we want to do here? For each parent node and a child node, we want to build a, an undirected graph, right? Basically, we're gonna create for the parent node, we want to append the child node, right, to it to its neighbors, right? Same thing for the child node. We also want to append the parent node as its neighbors because remember here, see here, so for 5, 2 is 5's child node, right? But for 3 is for 3 is 5's parent node, right? So that's why we need to build a double link, double directions graph here. So right append node, right? Same thing for the left here, right? Graph node append node left, and graph node dot left append node, right? So now we have a graph with with each node with its parent, right? With its neighbor's node. So now we just need to do a breadth first search to the find all the nodes that have this distance. And since we're doing a breadth first search, we're gonna use another queue here, right? So yeah, we can reuse the same variables here. So, but this time instead of the root field, our starting point will be the target node, right? So which means in this case it's gonna be the target node, and then we're gonna have a distance here, right? To keep track of our current distance 0, right? Same thing here, right? While q is not it's not empty, we just do a node dot we pop the q, right? Pop the q, pop left, right? We pop left, and then for each node, for each child node, for neighbors, we can do a neighbors here. For neighbor in node no the graph, sorry. Yeah, sorry. So for the breadth first search, so first we since we're doing this search uh level by level, so first we have to we need to only process this level's node, right? Not the rest, not the next level. So we need to have a for loop here in the range, the length, right? So basically the current length will be the current level we want to process, the current queue, right? And for this one here, right? So and for each node here, we check first. Okay, so let me finish the breadth search code here. Then we do a queue for neighbors, right? For neighbor for in this graph So basically, we want to get all the neighbors for this node, and we'll be adding it to the queue, right? Graph that node, right? We want to add it, but okay, remember, so since it's a direct undirectioned graph here, so we don't want to end up with an infinite loop here. So we need to have another like variables to keep track of what are the nodes we have visited here, right? Because we don't want to visit this node more than one time, right? So here, and since we already have the target there, we're gonna add this target to this visited set first. So here in each node for each neighbors, if neighbor, right, neighbor it not in set, right? So if it's not in that visited set, what do? We add, right? We add this neighbor to this queue. That's our current levels append. That will be the next level. That will be the next level's node, right? So, and once we do that, we also need to add this neighbors to this visited set, right? And in the end here, we will increase, right? We increase the distance by one, right? Since we already finished the current levels process, we need to increase this one by one. That's how we do the breadth first search for this graph, right? And so when do we stop, right? I mean, so now we have to stop somewhere, right? So the first thing is while q is not equal and, right, distance, right? Once we reach the distance, right? If the distance is greater than k, then we know we don't need to keep we don't need to traverse anymore because all the rest node will have the distance greater than k, which we don't need, right? So and and here, right? So and every time when we have a node here, what do? We check, right? If the distance is equal to k, right? If that the current distance is the k, then we know all the nodes have the set. With this distance is the result we need. Sorry, we need to also have a result array here, right? Array dot append, right? And then do a distance sorry, current node. Yeah, yeah. And then in the end, we just return the result, right? I think that's pretty much it is, if I didn't make any stupid mistakes here. Append. Yeah. Uh, yeah, sorry. So because, yeah, I think this is because we need the value the value of the node, not the node itself, right? So here when we append the final result, we need to get its value, not the node. Yeah. Okay. Yeah, since the order doesn't matter, so as long as they have all the answers there. Cool. Yeah. So it passed. So just to recap real quick. So since we don't know where this target node is, right? Instead of considering the left, the right, okay, so what are the nodes before above it? What are the nodes under it? It's we should convert this tree to a graph. So that's our first step. We convert the tree, do a pre-process, a pre-order traverse, and convert it to a graph. And then the problem is converted to find all the nodes that have the k distance with this target node, right? That's a regular breadth first search for a graph. And then in the end, we just return the result. Uh, cool. I think that's it. That's it. All right. Thank you for watching, guys. Let me know, comment, yeah, if you want Want me to do another problem? Yeah, let me know. Yeah. If not, I'll just keep my on my own pace to do some other problems. Yeah. While I'm learning the LeetCode problems. Cool. Thank you guys.